Welcome to today's lecture on satellite communications. In the last two lectures, we have discussed about wireless communication. First of all, it was wireless LAN, which can give you coverage over a small geographic area. Then we have discussed the cellular telephone network, which can give coverage over larger area, maybe a country. Today we shall discuss about another communication system which can give you global coverage, and in all the cases, as we have seen, there is always broadcast communication where it is necessary, where a medium is shared by a number of stations. So, you have to use medium access suitable medium access control technique. And here is the outline of today's lecture. First, I shall discuss about some of the important concepts related to satellite communication. MEO satellites and its applications, geo satellites and its applications, and finally, I shall discuss about the medium access control techniques used in satellite communication. And on completion, the students will be able to explain different types of satellite orbits. They will be able to explain the concept of footprint of a satellite. They will be able to specify the categories of satellites, and they will be able to specify the frequency bands which are used in satellite communication, and they will be able to explain the uses of different categories of satellites, and finally, they will be able to specify the MAC techniques used in satellite communications. So, first we start with orbits. Although the number of orbits is very large in satellite communications, but they can be broadly categorized into three types, and the three types are equatorial. As you can see here, this is the equatorial plane, and these are the poles. This is your earth, and here is your the orbit. So, it is on the equatorial plane. Then it can be inclined with respect to the earth polar line, vertical axis, or it can be polar. So, orbit can be more vertical in this direction, that means polar orbits. So, you can have three different types of orbits, and as you know, the time required to make a complete trip around the earth known as period. That means, the time required to make a complete trip is known as a period. We are all familiar about the natural satellite, that is moon, and the period is known to you, and but here we are talking about the artificial satellites. And as you know, the time required to make a complete trip around the earth, which is known as period, is determined by Kepler's law of period. There are several laws, but the Kepler's law of period specifies that period t square is equal to 4 pi square by gm into r cube, where t is the period, g is the gravitational constant, m is the mass of the central body, that is earth, and r is the radius. You see, this radius is different from the altitude from the surface of earth. So, whenever sometimes the radius of the orbit is given, sometimes the altitude is given, we have to you have to understand the difference between the altitude and the radius. Obviously, the altitude will be lesser than the radius. And so far as the footprint is concerned, signals from different satellite is normally aimed at a specific area called footprint. So, here as you can see, a satellite is covering a very large area in this particular case. So, it can cover a very large area, and power is maximum at the center of the footprint. Obviously, the power will be maximum here in the central part, and as you go towards both sides, it will decrease. That means, it decreases as the point moves away from the footprint. Now, nowadays different types of antennas are used in satellites, and these are all electronically controlled. And for example, if phased array antenna is used, then the footprint can be dynamically changed. It can be small, it can be large, it can be controlled. So, the footprint can be changed. For example, here the footprints are small, as you can, as it is visible here. So, this part and this part. So, these are small, and another possibility is that on a particular spot the beam can be focused for some duration, which is known as the dwell time. So, the amount of time a beam is pointed to a given area is known as the dwell time, and of course, whenever it changes from one position to another, it takes some time, and the time is of the order of microsecond. So, the dwell time should not be very short or should not be very large. So, dwell time is controlled electronically, and it can be focused on some parts for certain period of time, and that time is usually of the order of few milliseconds. So, this is the dwell time, and so we find that there are two important concepts. One is footprint, another is dwell time in the context of satellite communication. Now, let us look at the different types of satellites that are used for communication. This is the surface of the earth, and it was that first satellite that was launched by the Russians, Sputnik, and after Sputnik was launched, there was the discovery of Van Allen belt. Van Allen belts are essentially where there is high energy charged particles, protons, high energy protons are available, and there are two such Van Allen belts, as you can see. One is here about 3000 to 5000, and another is from above 15,000. So, there are two Van Allen belts which are, and obviously, if satellites are placed in these regions, then they will be destroyed by the high energy particles. So, satellites are placed avoiding these two Van Allen belts. For example, the low earth orbits which are in the region, I shall show you another diagram which will give you better picture. For example, this is the earth, and the low earth orbit LEO satellites are positioned between 500 to 2000 kilometer. As you can see, this is the orbit. So, the altitude is 500 to 2000 kilometer. On the other hand, the medium earth orbit, which is between two Van Allen belts, is from 5000 to 15,000 kilometers. These are known as medium earth orbits or MEO satellites, medium earth orbit satellites. And there is third orbit, which is known as geostationary earth orbit, GEO. So, that is at the precise distance of 35,786 kilometer. So, these are the three popular orbits which are used for placing satellites. However, there is another one in between MEO and the geostationary orbits, that is your GPS, global positioning system, is another constellation of satellites which are placed at a distance of 20,000 kilometers. So, obviously, it is above the second Van Allen belt, but definitely much lower, much below the geostationary earth orbit, which is at the distance of about 35,800 kilometer. Okay. So, as I mentioned, these orbits are chosen such that the satellites are not destroyed by high energy charged particles present in the two Van Allen belts. So, we find that we have broadly three types of orbits. Now, let us look at the frequency bands used in different in the satellite communication. This is in the microwave range. We have already discussed about it, microwave, and where line of sight communication is performed. Line of sight communication, and there are several frequency bands. L band, which uses two frequency bands, one is for downlink, another is for uplink. So, frequency is in the gigahertz range. So, downlink frequency is around 1.5 gigahertz, uplink frequency is around 1.6 gigahertz. S band, where the downlink frequency is around 1.9 gigahertz, uplink frequency is around 2.2 gigahertz, and this is the bandwidth available for data communication. And C band, which is very popular and widely used in geostationary satellites, is 4 gigahertz and 6 gigahertz. 4 gigahertz is downlink and 6 gigahertz is uplink. Then these bands are gradually becoming congested, and presently Q band is widely used, and the Q band has got downlink frequency of 11 gigahertz and uplink frequency of 14 gigahertz, around that. And then once the Q band gets exhausted or fully utilized, then we have to go for K band, Ka band, which is in the range of 20 gigahertz for downlink and 30 gigahertz for uplink, and which can give you very high bandwidth 3500 megahertz. So, we find the frequency bands, and as I mentioned, in all cases it is line of sight communication and it is in the microwave frequency range. Now, let us consider the low Earth orbit satellites. The low Earth orbit satellites is in there are several examples. Essentially, a single satellite is not used. A constellation of satellites very similar to cellular telephone network are used that work together as a network. So, not a single satellite, but a constellation of satellites, a number of satellites are used in the low Earth orbit to form a network. Usually in LEO satellites, polar orbits are used, that means in the range of 500 to 2000 kilometers. So, altitude is 500 to 2000 kilometer, not the radius, and typical value is 850 kilometer, and the period based on this altitude you can find out the time period, which varies from 90 to 120 minute, and for example, for 850 kilometer altitude the period is 100 minute, and the satellite rotates at the speed of 20,000 to 25,000 kilometer per hour. And whenever a satellite is placed at this altitude, the footprint can be 8,000 kilometer diameter, and of course, you can focus over a narrower area, but this will be the maximum radius, because because of line of sight communication and Earth's curvature, the footprint cannot be very large, and higher the altitude, the diameter of the footprint, the area that can be covered area can be larger. And the LEO satellites can be broadly divided into two types. First one is known as little LEO. In little LEO, they communicate at less than 1 gigahertz range. For example, we have seen that less than 1 gigahertz range is when they do not use L band, lesser than that. Then the big LEO uses 1 to 3 gigahertz. One notable example is Iridium, we shall discuss about it. And the third category of LEO satellites is known as is used for broadband internet access, and one notable example is teledesic. I shall discuss more about these two systems, Iridium systems and teledesic systems. Let us first consider how they communicate. In case of low is the footprint and this is the footprint of the another satellite. And as you can see, the this satellite can communicate with this satellite, another satellite, and also the ground stations or gateway links. So, this is known as GWL, that is your gateway link, and third is your user mobile link. So, directly the mobile phones can communicate with the satellite in this case. So, there are three different types of links which are used for communication: ISL, GWL and UML, user mobile link, gateway link and inter-satellite link. And let us consider in little more detail the Iridium system. This project was started by Motorola in the year 1990 with the objective of providing worldwide voice and data communication service using handheld devices. So, the basic objective was that with the help of the satellite, people should be able to talk to each other, and that will cover a very large geographic area. And of course, it took quite some time to materialize the project, and after about 8 years, it materialized with 66 satellites. And although the project started with 77 satellites initially, it started with 77, and because of this initial number was 77, the name Iridium has been taken, because Iridium is the 77th element in our periodic table. So, the name has been taken from this, but unfortunately, the number of satellites got changed, but the name has been retained. So, using 66 satellites, these are divided into 6 polar orbits. So, you have got 11 satellites in each orbit. As you can see, each orbit has got 11 satellites, and you have got 6 orbits, 1, 2, 3, 4, 5 and 6. So, you have got 6 polar orbits rotating around the earth and at an altitude of 750 kilometer, which is not far away from earth's surface. And in each orbit you have got 11 satellites, and each satellite has 40 spot beams. So, the footprints of different satellites are shown here, and total of 3168 beams are possible. However, all are not used. Around 2000 beams are actually used, although possible spot beams are 3168 beams. So, it can cover small geographic area at a time, and by controlling the dwell time, different spots can be covered. So, in this way the whole earth can be covered by using this constellation of 66 satellites used in Iridium system. Then another important notable system that is worth mentioning is teledesic system. So, it started with a very ambitious project and by Craig McCaw and Bill Gates in the year 1990. In the year 1990, with the objective of providing fiber optic like communication facility. We have seen the Iridium project was developed with the objective of providing voice communication and at most low bit rate data communication. But this teledesic project was developed with the objective of providing data transfer at a much higher rate, very similar to fiber optic like communication. In other words, to provide broadband service. And this teledesic system ultimately was designed with 288 satellites in 12 polar orbits. So, there are 12 polar orbits, very similar to the Iridium, and there are 228 satellites. So, you have got 24 satellites in each orbit, and you have got 12 such polar orbits, and these are stationed at an altitude of 1350 kilometer compared to 750 kilometer of Iridium. And the communication is being done by using the Ka band, and at a particular instant 8 neighboring satellites communicate with each other by using ISL, inter-satellite link, and GWL is used between a satellite and a gateway, and also the user mobile link is being used for communication between an user and a satellite. And as we have already discussed, satellite focuses its beam to a cell during a dwell time, and it allows data rates of the order of 155 megabits per second for uplink and 1.2 gigabits per second downlink. I think such a high data rate is quite sufficient for any type of communication, both voice, video and data, and that is why we are telling that teledesic system is being developed to provide fiber optic like communication, but it has the potential to cover the entire earth with the help of a with 288 satellites. Now, let us consider the MEO satellites. These MEO satellites are positioned between two Van Allen belts, as we have discussed, at an altitude, typical altitude is 10,000 kilometer and period is 6 hours, not minutes. As you can see, as the altitude is increasing, period is also increasing. So, it is 6 hours is the period for typical MEO satellites. And as I mentioned, global positioning system or GPS is possibly one of the very popular satellite system used nowadays, and this has been developed used for satellite based navigation system, and this comprises a network of 24 satellites at an altitude of 20,000 kilometer with a period of about 12 hours. That means twice in a day a particular is visible by a particular from a particular location, and it has the inclination of 55 degree. So, this was originally intended for military applications. That means, this particular satellite systems was developed by Department of Defense of USA, and original plan was to use it primarily for military applications, but in the year 1990 they changed their policy and it was made available for civilian use. And with the help of this GPS system, one can do global positioning, and from that it has derived its name. Actually, it allows land, sea and airborne users to measure their position. That means, 3-dimensional position can be measured, velocity can be measured, and the exact time also can be measured with the help of a GPS receiver. So, a GPS receiver has been found to be a very invaluable tool to the captain of a airplane, to the captain of a ship, and also for very soon it will be used by people who will be traveling on road, vehicular traffic. So, every car owner, every ship owner, every pilot in the aircraft will be having such a receiver, and not only the position, the velocity and time can be very accurately measured, and the accuracy can be within the range of 15 meters, and that is the reason why it is one of the most widely used satellite for measuring the position, velocity and time. This global positioning system, actually measurement is done with by using it is used for land and sea navigation using the principle of triangulation. So, here you have got 3 known positions A, B and C. These are the 3 positions of a satellite, and the position one, this is one unknown position. It can be proved that if these 3 positions are known, the position of the point of unknown position can be identified with the help of suitable device. So, that is being done with the help of a GPS receiver. So, by time stamping, the signal is sent to A, B and C, and the delay is measured, and by which the distance of A, B and C is measured, and then the point at which these three diameters coincide, that is the exact position. And the another satellite is used to provide the time. That means, these GPS satellites each having four very accurate clocks based on that nuclear material. So, those clocks gives very accurate time. So, the fourth satellite provides you the very accurate time, and the other three satellites gives you the exact measurement of distance, and with the help of that one can very accurately position the distance, time, and the speed of a particular vehicle or a airplane or a ship. So, the requirement is that at any point of time at least 4 satellites should be visible from to the user or from any point of the earth. It is not necessary that it has to be on any point of the earth, it can be in space also. For example, from the aircraft also it can be used. So, a GPS receiver can find out the location of a map. So, nowadays there is no need to use the compass, but you can use GPS receiver for the purpose of positioning. In fact, this was widely used in Persian Gulf War for identifying the position of different vehicles used in war. So, this is your GPS. Now, let us focus on the geosatellites. So, to facilitate constant communication, the satellite must move at the same speed as the earth, which are known as geosynchronous satellites. We have seen in case of MEO and LEO or even in GPS satellites, the satellite is moving around the earth, and from a particular position if you look at it, you will find its position keeps on changing. So, you have to keep track of it, you have to compensate for Doppler effect and other things you have to do. But if it is positioned, if it is so positioned that its movement is stationary with respect to a point on the earth, then it is called geostationary geosynchronous satellites. And there is a special situations when the geosynchronous satellites are on the equatorial plane. So, if it is on the equatorial plane, then it is called geostationary satellites. That means, geostationary satellites are special case of geosynchronous satellites when the plane is on the equatorial region. So, it uses the equatorial plane to place the satellites, and obviously, you have got 360 degrees, and with the present day technology you can use up to 180 satellites in the equatorial plane, and with the help of that you can do communication. And as I mentioned, the altitude is 35,786 kilometer and radius is 40,000, about 42,000 kilometer. That means, from the center of the earth the radius is 42,000 kilometer, but the altitude from the surface of the earth, it is from sea level, it is 35,786 kilometer, and period is exactly same as the rotation of earth, that is your roughly 24 hours. And as I mentioned, the orbit is on the equatorial plane, and as I mentioned, you can have at most 180 geosatellites based on the present day technology, and by using Ku band of whenever Ku band is used, then you can have up to 180 satellites, but as you go for Ka band, the number of satellites can be increased. Although you can have 180 satellites on geostationary, you can have 180 geostationary satellites, the whole globe can be covered only by using 3 satellites. As you can see, with a particular satellite roughly covers 1/3 of the earth. So, if one satellite covers 1/3 of the surface of earth, then by using 3 satellites the entire earth can be covered. In other words, with the help of 3 geostationary satellites, it is possible to have global communications from any place on the earth to any other place on the earth. Communication can be done with the help of 3 geostationary satellites. Now, let us look at the key features of the geostationary satellites. One important feature is the long round trip propagation delay, and as you know, the distance is about 36,000 kilometer, and even with the speed of this with the speed of light, that the electromagnetic radiation goes from the surface of earth to the satellite and comes back, and the speed is 3 into 10 to the power 8 kilometer 3 into 10 to the power 8 meter per second. So, even with that speed, it takes about 270 millisecond between two ground stations. That means, the round trip delay is 270 milliseconds. Then while designing system, you have to take into this parameter, particularly as we shall see when we shall consider the medium access control technique. Secondly, it is an inherently broadcast media. So, it does not cost much to send to a large number of stations. Now, we are familiar with our conventional telephone systems. We use local calls, then as the distance increases, the cost of communication increases. That means, whenever you use STD calls, or whenever you use if you put a call to USA, you have to pay more. That means, the cost of communication increases with the distance, but that is not true in the case of satellite communication. The cost of communication is same irrespective of the distance between 2 points. However, it suffers from low privacy and security, and for that reason suitable encryption technique is essential to ensure privacy and security. So, this is a very important aspect of communication. Then finally, as I mentioned, the cost of communication is independent of distance. So, you have to take into account these features, and you have to exploit them, and one of the system where it is widely these features are exploited is VSAT, very small aperture terminal. Let us look at it. VSAT stands for very small aperture terminal, and this normally the antenna of a ground station has to be several meters in diameter, and as a result the cost of the antenna and the communication system is quite high. But to make it affordable to common people, that means this VSAT terminal was developed to make access to the satellite more affordable and without an intermediate distribution hierarchy. That means, direct communication can be done directly with the satellite, at the same time it has to be made affordable to the common people. With that objective, VSAT very small aperture terminals were developed, and for example, most VSAT systems operate in the Q band, KU band, with an antenna diameter of only 1 to 2 meters. So, that is very small, relatively small compared to the bigger antennas that is being used in traditionally used, and it requires only transmitting power of 1 to 2 watts for communication. So, this can be easily this is quite neither the power is very high nor the diameter is very high. It can be very easily used in houses. So, there are several implementation approaches, particularly they can be categorized into 3 types: one way, split two way and two way, and we shall discuss in more detail the one way and two way. The split two way is a little special situations where VSAT does not require uplink transmit capability, which significantly reduces cost. In split two way, what is being done, the satellite only sends data in the downward direction using broadcasting or some other technique. Then there is no uplink transmission from the ground station to the satellite, and that communication is done with the help of some other system. It can be PSTN, public switch telephone network, or cellular telephone network, or whatever it may be. So, that is how it is a split two way systems where which does not require uplink transmit capability, that makes it simpler. So, this is used in many situations. Let us now consider the other two, the one way and split two way communication system and the two way communication system. In one way VSAT configuration, it is essentially simplex communication. We know that in simplex communication is only in one direction, and that is what is being done in this particular case. Here for example, there is a master station, it sends data to the satellite and satellite relays it over a large geographic area. So, it is essentially the broadcast coverage area, and all the ground stations in this area can listen to what is being transmitted by the master station through the satellite. So, the satellite here just acts as a relay in the sky, and it is used for broadcast satellite service. That means, whenever something has to be broadcasted, then this type of simplex communication can be used. For example, as we shall see, the satellite television distribution system uses this type of one way communication. Here for example, here is the studio of the TV Doordarshan, and here is the uplink earth station, and for the uplink earth station, by using key band KU band uplinks the signal, then the satellite sends it to a number of cable TV service providers. So, the cable TV service providers have antennas located in their place, and then the cable TV operators distribute the television signals to a number of houses. So, this is the KU being uplink, and here is the KU band downlink signals, which are being received by the cable TV operators, and then they distribute it to the households. So, this is a satellite television distribution system. Nowadays, another important service is becoming popular, that is your direct to home DTH service, which is being publicized by our Doordarshan. So, in direct to home service, in the household, one can put an antenna which has the diameter of less than 1 meter, and then by using one set top box directly from the satellite, the digitized television signals can be captured, and then one can put it on the TV. So, by bypassing the cable operators, nowadays by using the direct to home service, this type of one way communication is being used for television distribution, television signal distribution. And although I have shown one large geographic area, you can have one small group also, a small group which requires some specialized service, that is also possible in one way VSAT configuration. Now, let us look at the two way VSAT configuration. In this two way VSAT configuration, all the traffic is routed through the master control hub. Actually, the VSAT antennas are small in size, and also the power of transmission is small. So, because of low gain antennas and small power that is being used in VSATs, direct communication between two VSATs is not possible. So, a master control station is being, which is also known as hub. So, in this case, the configuration is somewhat like this. This is your satellite. So, we can say this is your satellite. This is your satellite. Then you have got your that VSAT and that hub, and you have got a number of VSAT antennas. So, it is like a star. So, all the VSAT hubs are communicating through this master control station or hub. So, this hub is acting as at the center of the star topology, and the communication is done in this way. So, this is the star topology that is being used. However, nowadays with the advancement of technology, it is possible to have direct communication between two VSAT antennas. So, in such case, each VSAT has the capability to communicate directly with any other VSATs. You do not require a hub. So, this one can be considered as the mesh topology. Although the satellite is there, is being used as the via media, but here say suppose this is one VSAT, this is another VSAT, this is another VSAT, this is another VSAT, this is another VSAT, all of them can communicate with each other. So, it forms some kind of mesh network since they can communicate with each other. So, it forms a mesh. So, we can see it is a mesh type of network that can be formed, and although VSAT is there which is used as via media. So, this is two-way VSAT configuration using mesh topology. Now, you require medium access control protocol for satellite communication. Why you require is explained here, and it is a very important design issue in satellite communication, particularly how to efficiently allocate the transponder channels. As you know, each satellite is having say 12 to 20 transponders, and each using each transponder the communication can be done with the earth stations. Now, in satellite communications, as you know, from the satellite to the earth station it is essentially a broadcast type of communication. So, there is no need for medium access control. However, as you can see, by using the same frequency band, uplink frequency, the ground stations are simultaneously communicating to the satellite, and as a consequence this uplink channel is shared by all the earth stations that is communicating with the satellites, and that requires medium access control. And there are many medium control techniques are used based on the environment and application, and they can be broadly categorized into the following types. First one is fixed assignment protocol. In this case, the number of users is small, so you can use fixed assignment. And another approach is demand assignment protocols, which is known as DAMA, demand assignment multiple access, and in some situations you can use random access protocols, or it can be a hybrid of random access and reservation protocols. Finally, they can be either distributed or centralized control. Now, we have already discussed about the medium access control techniques for satellite communication. As you know, that collision based medium access control technique cannot be used because of long round trip delay. Also, we cannot use token passing based techniques. So, only possibility is to use Aloha or slotted Aloha and the reservation based protocols. Let us see what are the different types used. And as I have discussed, we can use FDMA, TDMA and CDMA depending on various applications. And FDMA provides the simplest communication, because here there is no need for synchronization, there is no need for collision, no question of collision. However, when TDMA technique is used, you have to do synchronization, because at different time slots, different channels, channels can be used in different time slots for communication, and there can be collision if two stations, ground stations, send signal simultaneously. So, synchronization is necessary, and there is a possibility of collision in TDMA, but that can be resolved. And another approach that can be used is CDMA, where it is possible to have parallel communication using the same channel and at the same time, and as you can see, n stations can communicate with each other. So, CDMA, TDMA and FDMA, these are all used in satellite communications. Let us look at the contention free medium access control protocols. First one is the fixed assignment protocols using FDMA. As I mentioned, FDMA is the simplest one. They allocate different frequency band to different ground stations, and communication can be done in parallel using different frequency bands. Or you can use TDMA, and this allocation is possible. Allocation of channel assignment is static, so it is fixed. So, it does not change with time, and this is suitable when the number of stations is small. So, when the number of stations is small, permanently some frequencies or time slots can be allocated to the ground station, and this provides you deterministic delay. In spite of the long propagation delay, this delay will be deterministic because there is no collision here, and which is important in real time applications. On the other hand, this demand assignment based protocols DAMA is suitable when the traffic pattern is random. That means, a particular station, ground station, sends for some time, then waits for quite some time. That means, when the traffic is burst in nature, in such a case you have to use random assignment based protocols, and particularly when the traffic pattern is random and unpredictable. And efficiency is improved by using reservation based on demand. The reservation process can be implicit or explicit. We have already discussed, and I shall give you a quick summary. And here, as you can see, how TDMA can be used. We know that it is at the time slots are divided, the time is divided, it is divided into time slots, and a frame is done. Here in this particular case, a frame has got 4 time slots. So, you can see different ground stations are sending at different time slots. So, this is being sent. So, this one is being sent by one ground station. These packets are being sent by another ground stations. These packets are being sent by another ground stations, and this is the TDMA stream which is broadcasted by the satellite towards all the ground stations. So, you can see it is following the same order, first this one, then this one, then this one. So, the same order is being followed, this followed by this, this followed by this, followed by this. So, and this is being repeated one after the other. So, this is how the TDMA works. And in case of random access based MAC protocols, as I have already mentioned, we cannot use collision detection multiple access protocol, cannot be used. So, it has to be either pure aloha or selective reject aloha or slotted aloha, and with this you can combine reservation. So, it can be reservation R aloha or reservation aloha, or sometimes a combination of random access with reservation access protocol. So, these are used to, this hybrid technique is used to have advantages of both random access and time division multiple access. Let us quickly have a recapitulation of the techniques that we used. We have already discussed in detail that reservation aloha, that is being used when the number of ground stations is larger than the number of channels. So, the reservation is done by directly trying to send in different slots. So, this is called reservation aloha. So, there is a possibility of collision in different slots, but once a station is able to transmit in a particular slot, so in the subsequent slot the same station will send. However, if a slot is free right now, and in the next frame 2 stations can send, so there will be a collision which has to be overcome. And another technique is used whenever you have when the number of stations is smaller than the number of slots, then you have got implicit allocations. So, this is 1 slot per station, since this number of stations is small, implicit allocation is there, and then the excess slots can be accessed by using reservation aloha or slotted aloha. That means, this part has to be it is acquired by contention based techniques. This is binder scheme, and in Roberts scheme, as we know, a separate slot is being used which is known as reservation slot, which is used for the purpose of establishing reservation, performing reservation, and then data can be sent in different slots. And then there are centralized medium access control protocol. The centralized FDOMA is extension of Roberts protocol. Here there are 6 reservation mini slots, as you can see, of variable length, but here there is one of the ground stations acts as some kind of master and which does the reservation, and variable length data can be transferred in this fixed priority oriented demand assignment. And finally, you have got packet demand access multiple access, packet demand access multiple access protocol PDA-MA, where there is a leader, and this leader control, you have got leader control slot, then guard slot. In leader control slot, acknowledgement is given to other stations about the reservation of slots, and this guard slot is being used as a gap, so that the ground stations get some time before reservation can be performed from the next time frame. And these are the information subframe where the transmission is performed based on the reservation. So, this gives you a quick summary of the medium access control techniques that is being used for satellite communication. So, before we discuss about the questions for this lecture, let me summarize about the different techniques, different systems where medium access control techniques are used. First, we have discussed about the local area networks, where we can use the contention based protocol like CDMA, CSMA, CD, collision carrier sense multiple access with collision detection, and also you can use token ring. And we have seen their applications in Ethernet, fast Ethernet and gigabit Ethernet techniques. And then we have discussed wireless LAN, where a collision is avoided by using a protocol known as CSMA-CA. And then we have discussed the satellite cellular telephone networks, where FDMA, TDMA and CDMA are used. And now in today's lecture we have discussed about the satellite communication system, where we have seen how various techniques, medium access control techniques are used for sharing the communication channel. So, here is time to discuss give you the questions for this lecture. First question is, distinguish between footprint and dwell time. Second question is, explain the relationship between the Van Allen belts and the three categories of satellites. Third question is, explain the difference between the iridium and teledesic systems in terms of usage. Fourth question is, what are the key features that affects the medium access control in satellite communication. Fourth question is, what are the possible VSAT configurations. Now it is time to give you the answer to the questions of lecture number 31. First question was, what is the relationship between a base station and a mobile switching center? Answer is, a number of base stations are under the control of a single mobile switching center. A base station is equipped with a transmitter receiver for transmission and reception for transmission and reception with the master stations in its footprint. On the other hand, the MSC, the master that coordinates communication among base stations and the PSTN network. It is a computer control system responsible for connecting calls, recording calls and also do the billing. Second question was, what is reuse factor? Explain whether a low or high reuse factor is better. Actually, the fraction of total available channels assigned to each cell within a cluster is known as the reuse factor. So, if you have got n cells in a cluster, then the reuse factor is 1 by n. Capacity of a cellular telephone system depends on this reuse factor. So, as the reuse factor increases, then you have got larger number of cells. So, you can the covered area in each cell decreases. On the other hand, if the n is small, then the area is larger. Third question was, what is AMPS and in what way it differs from DAMPS? AMPS is your advanced mobile phone system, is purely analog cellular telephone system developed by Bell Labs, and primarily it was used in North America and some other countries. On the other hand, DAMPS is a backward compatible digital version of AMPS. We have discussed about the DAMPS in the last lecture in details. Fourth question was, what is mobility management. Mobility management deals with two important aspects, handoff management and location management. Handoff management maintains service continuity, as you have seen when a mobile station migrates out of its current base station into the footprint of another base station. To do this, it is necessary to keep track of users' current location, that is being performed with the help of location management. So, location management and handoff management together performs the mobility management. Fifth question was, what is the maximum number of callers in each cell in a GSM? As you know, in a multi-frame used in GSM, 8 users can transmit in 8 slots, and there are 124 such channels which are sent simultaneously using TDMA. So, the total number of callers in a cluster is 124 into 8, and as the reuse factor is 7 in GSM, the maximum number of callers in a cell is 124 into 8 by 7, that is roughly equal to 141 or 140. Sixth question was, distinguish between soft and hard handoff. As we know, in case of hard handoff, a mobile station communicates with only one base station at a time. So, when it moves out from one base station to another, first it breaks connection with the existing one before establishing connection with the new base station. On the other hand, in soft handoff, a mobile station can communicate with two base stations simultaneously, and gradually the control is transferred from one base station to another base station. So, with this we come to the end of today's lecture. Thank you.